My name is Kennedy Kibetu. I'm the technical engineer at Jubilee Brew Solar, based in Nairobi, Kenya. Before we start this webinar, I'd like to put up a survey and kindly fill it in as we wait for more people to join us. Kindly fill in this survey. Then we'll get on with the webinar. Kindly let me know in the comment section if you are able to hear me. Let me know if you can hear me, please. For the rest that are joining, kindly fill in the survey that is on your screen, and then we can proceed. I'll have the survey up for another 3 minutes or so as we wait for more people to join us. All right, thank you to everyone who's joined and who's filled in the survey. For those who have just joined us, my name is Kennedy Kibetu. I am the technical engineer at Jubilee Brew Solar, here based in Nairobi, Kenya. And today's topic is on lead carbon batteries. This is a fairly new battery technology that is coming into the market, and we are proud as Jubilee Brew Solar to be among the first companies to bring in this new product. As we go through the webinar, we'll first start with the different types of battery chemistries and then introduce the lead carbon batteries. So start with a brief introduction as to who Jubaili Bros is. So Jubaili Bros Solar is a division of Jubaili Bros, and Jubaili Bros has been a leading provider of power solutions in Middle East and in Africa. And you can see from the chronological order below as to when and how and where the company has been expanding to. So starting in Lebanon in 1977, then to UAE, Nigeria, Afghanistan, Kuwait, Ghana, Qatar, um, Uganda, South Africa. So this primarily was mostly generator sales and distribution. However, in 2017, that is when the solar division was started. And from there, we've continued to expand into Pakistan, into Kenya, and now looking forward to more and more regions. And our main aim is to provide our solar EPCs in all these regions with leads, with training, engineering support, product supply, referral to finance, as well as technical support in the field. This is a global logistics reach. As I had mentioned earlier, um, Jubaili Bros is based in the Middle East and Africa and dealing majorly with sub-Saharan Africa. So you can see from this map that everywhere where we have a flag, we have a company, sister company, distributors, and customers. So you're guaranteed, even in this logistically hard places to reach, Jubaili Bros and Jubaili Bros Solar will be able to get you products regardless of the region that you're in. Next is the 6 pillars that we have for supporting our EPC customers. We have product supply. So from our distributors' warehouses, for all the products that we do supply, you'll be able to get the products that you need for your projects. This is throughout Middle East and Africa, and we are able to provide quick delivery. Next is training. This is one of our key initiatives, and this weekly webinars are part of this training pillar, where we provide clients with technical knowledge uh, from design, installation, commissioning, O&M, and uh, anything regarding the solar side and solar projects. We do offer training. Other than the weekly webinars, we do have bespoke trainings that some of our clients might want, and we are able to provide that for them. Then we have engineering support, where we have engineers who have specialized in different aspects of um, the solar space, from design, installation, commissioning, and O&M as well. And we're able to provide that engineering support to make sure that you are operating at a reduced levelized cost of electricity, meaning we want to optimize your designs, making sure that you have the best equipment and the best effectiveness in your projects. Then we offer leads. We are not an EPC. However, we have connections with EPCs in the market, and we are able to identify and pass along opportunities to our EPC customers. Then we have referral to finance, where we can connect our EPC customers with financing institutions, and they are able to find financing options for their customers for their solar systems. And then lastly, we have after sales support, where we have our engineers who can assist with site support, from commissioning to O&M, as well as timely warranty support. So with these 6 pillars, you're guaranteed from the very beginning of your inquiry about a product or about a project, the technical aspects of any product and project. We're able to lead and guide you from the very beginning, from the inquiry to design to installation and to O&M, as well as offering warranty support for the products and the services that we offer. Now we'll go into the lead carbon batteries, but we'll start with a look into how the battery industry looks worldwide. So we have different battery chemistries, and this is the different mechanisms or how energy is stored in different energy storage devices. So here we have 5 examples. We have mechanical energy storage, and this can be through pumped hydro storage, compressed air storage, or the flywheel. Then we have electrochemical storage options, and this is where most of the batteries that we've interacted with are, where we have lead acid batteries, we have lithium-ion batteries, we have the lead carbon batteries, and then we have flow batteries as well. Then we have electrical, where we have examples of supercapacitors. Then we have chemical, where we have hydrogen and fuel cells, which are in this category of the chemical energy storage systems. And then we have thermal energy storage systems. And an example is molten salt. So depending on the size and storage quantity that you're looking for, you have different ways of having energy storage. So this is an example of mechanical batteries. We have a flywheel, we have compressed air, and we have pumped hydro. So this depend on the mechanical aspects, moving, for example, water from, in the case of the pumped hydro, pumping water up into a reservoir, storing that, and then when it is needed, the water is released, flows down, and turns a turbine. So when it's pumped back up into the reservoir, the water acts as a battery since it's storing um, energy in potential form. The same with compressed air. You have compressed air can be released, turn a turbine that turns a generator that provides electricity. However, you can have a system that extracts air from the environment and pumps it into the ground to form a battery. So this could be either through PV, through wind, through the grid, that is then used to turn a motor that turns a compressor and that pumps air into the ground. So the compressed air chamber acts as a battery that can then be released in another form of energy. Another now into electrochemical batteries, and this is the biggest range or biggest interaction we've had with batteries, from the normal lithium-ion battery that is in our mobile phones to batteries for our remotes, batteries for our vehicles, and now the lithium-ion batteries that are being produced for PV energy storage. So a broad category of the batteries that we have and we've interacted with are in this electrochemical range. From the simple household devices we use to vehicles to PV storage, most of that will be found in this electrochemical category. Then we have supercapacitors, and this work on the principle of storing a high amount of charge that can be discharged very quickly and when is needed. So a supercapacitor is an example of an electrical energy storage system. Then we have hydrogen cells. This is in the chemical category where we have a fuel cell with hydrogen coming into the anode side, and then we have electrons moving between the anode and the cathode. So you have hydrogen coming in, and then the byproduct of this is water and oxygen. And from this now, and also another byproduct is heat. And from this interaction within the fuel cell, we have electricity being generated. So this is also a newer form of energy storage, and that is also gaining a lot of traction. Then we have thermal storage systems, and this is an example of a CSP plant, concentrated solar power, where we have thousands and thousands of mirrors that are reflecting the sun's rays onto a single spot that is on top of a tower. This spot contains molten salt that is heated by all this reflection, it's heated and becomes very hot, and this can then be channeled down to heat water, and that water is what is used to, that steam is what is used to generate electricity. So when it's at the top of the tower here, in its molten form, it acts as a storage system, and hence why this is considered a thermal battery. So this is a graph showing how different battery chemistries work with regard to how long they can hold energy and the amount of power that they can discharge. So we have from milliseconds up to seasons in terms of duration, and we have kilowatts to gigawatts in terms of power storage. So we can see supercapacitors can store charge or energy for only small amount of time. However, there are newer supercapacitors that are coming out that can handle um, energy for longer periods of time. However, they can also store a lot of energy. We can see here from about 5 kilowatts all the way to 10 gigawatts. We have flywheels as well that can also do short periods of energy storage from a couple of seconds to minutes, but they can also do large amounts of energy storage from around 10 kilowatts all the way to megawatt scale. Then we have electrochemical batteries. These are the batteries that we've all interacted with that can store charge from minutes up to days. And this is where you'll find your lead carbon, lead acid, lithium ion batteries in this range. And they can also be used from small energy storage capacities from watts, kilowatts, all the way to 100 gigawatts. Then we have the compressed air that is also in the very large energy storage scale, and they can also last for very long, from hours up to a couple of weeks. The same with pumped hydro that can also be from minutes up to several weeks. Then we have a new battery chemistry that is coming out, and these are graphene batteries that are also capable of storing very high amounts of energy and can hold that for very long periods of time. So depending on your energy requirements, you can find a storage system that works for you. Before I proceed, I'd like to say that I've enabled the Q&A mode. So if you have questions as we proceed, you can type them down and remember to mark them as a question so that I'll be able to see the question after we are through with the webinar when you go into the Q question and answer period. Looking at how the global battery market looks like, especially for electrochemical batteries, because these are the batteries that we interact with the most. We can see in 2020, we had about $90 billion for the electrochemical batteries, and this is expected to grow exponentially with an estimate of around $150 billion dollars in 2030. And this shows you that there is an increase in the demand for energy storage, and this is um, what is being projected to be the global market share for energy storage, especially electrochemical batteries. And here we can see the different battery types and how they are projected to rise in the market. We can see lead acid batteries. Comparing 2020 and 2030, there is a significant increase. And the lead acid batteries are the current largest segment and will continue to be the largest segment, given that they are the first batteries to go into when you're looking into energy storage for residentials, as well as a lot of vehicles use lead acid batteries. However, there's also an increase due to the rise in electric vehicles. And then one of the other reasons why we have such a, a huge leap with lead acid batteries, even compared with the other battery types, is because there is a mature technology in how these batteries are manufactured, meaning there is a mature supply chain and manufacturing as well. Hence why you can see um, a significant rise in lead acid batteries as compared to the other battery types. Then now we look at the different batteries in the electrochemical applications. So a few things to define before we go deeper. We have the cycle, and the life cycle of a battery is the number of charges and discharge cycles that it can complete without losing performance. So the lifetime of a battery is usually given in cycles. So you'll hear a battery has a life cycle of maybe 3,000 cycles. Another one has 10,000 cycles. So that shows you the number of cycles it can perform before losing performance. Then you have specific energy, and this is the energy per unit mass. So the amount of energy that is stored in the size of the battery. This can be quoted as kilowatt hours per size, and it is also known as energy density. So a high energy density or a high specific energy means that the battery can store a lot of energy in kilowatt hours in a very small size. Then you have specific power or the power per unit mass, also amps per size. It is known as power density. So we have energy density and power density. And the higher power density or specific power means that the battery can give a high current while occupying a small size. Then you have the depth of discharge, denoted as DOD, and this is usually expressed as a percentage of the total capacity of the battery. Discharging a battery entirely dramatically shortens the usefulness or the useful life and the lifetime of that battery. So with lead acid and lead carbon batteries, you'll see that you have a recommended depth of discharge of around 50 and 60%, meaning you are not supposed to drain the battery beyond 50% or 60% of its capacity. So we have lead acid batteries, we have lithium-ion batteries, supercapacitors, and then we'll look at the lead carbon batteries. We have lead acid batteries, and the lead acid battery is the most commonly used type of battery in PV systems. And its main benefits are because of the low cost and simple manufacturing, because we saw that it's a mature technology. It's a system that has been there for quite a while. They have high specific power. So we saw what high specific power is, meaning you can store a lot of amperes, a lot of power in a very small um, size. And they're also capable of high discharge currents. They perform well in low and high temperatures. That is why they are preferred a lot. And there's efficient recycling as compared to other battery types. Because of the maturity of technology, there have been ways to find better ways to recycle them. Then one of the biggest advantage is that you do not need a battery management system for lead acid batteries. So this is the internal composition of a lead acid battery. We have the protective case with the terminals, positive and negative terminal. And then now within um, the battery, we have the battery cells, where we have the cell divider separating the different battery cells. We have the positive electrode and the negative electrode. The positive electrode is a lead dioxide material, and the negative electrode is lead. And then we have the fluid that is contained within the battery. We have diluted hydrosulfuric acid. So in some cases, you'll hear flood type batteries, and these are the ones with the fluid. And then we'll have gel batteries, where now the fluid is replaced with a gel-like substance. So we have the advantages and disadvantages of the lead acid batteries. As we had seen, they are low cost and simple manufacturing, low cost per watt hour, high specific power that is capable of high current discharge, uh, good environmental performance, as well as no battery management system required. However, they have disadvantages, and that is why people are looking into more and more, or rather, different battery types. They have low specific energy. So we had seen what specific energy is, and it's the amount to store. It's the capability to store um, energy, kilowatt hours, in a small size. So they have very low specific energy, meaning you need a very huge battery to have a lot of energy stored. So poor weight to energy ratio. Slow charging, which can take 14 to 16 hours to charge the battery. Um, they need specific storage conditions to prevent uh, issues like sulfation. Then they have a limited cycle life because repeated deep cycling will reduce the battery life. That is why they have a very specific depth of discharge to operate, which is usually between 50 to 60%. Then we have watering requirements for the flood type lead acid batteries, where you need to continuously top up the fluid that is within the battery. Then there are transport restrictions as well for the flood type batteries, as well as due to the nature of the fluid that is contained in them, and the materials that are in the anode and the cathode, they have adverse environmental impact. Then we have the lithium-ion batteries. These are becoming the preferred type of battery for solar PV installations. And this is mainly because of the high energy density with a potential for higher capacities, meaning you can store, you can have a high kilowatt hour energy storage capacity in a relatively small battery. They have a low self-discharge rate. This is as compared to the lead acid battery, which will, when it's not in use, will discharge itself. The lithium-ion batteries have a low self-discharge rate. They have low maintenance. You don't need to have any watering conditions or anything to do with maintenance, only just checking the terminals that they're okay. And then they have a long cycle and extended shelf life, with and some even having cycle life of 10,000 cycles. So assuming that you are doing one cycle a day, you can see how long this battery will last you. So it's over the recent years, they've become the popular choice and have overtaken the lead acid batteries as the preferred option, especially for home solar systems. So this is how the costs for lithium-ion batteries have continued to decline over the years. We can see from 2010, we've gone to about a 13% decline. And this is due to the popularity of the lithium-ion batteries being in our everyday devices. We have the mobile phones that we use using lithium-ion batteries, and this has seen a significant reduction in the cost. Also, with the emergence of electric vehicles, this has also brought the cost of lithium-ion batteries lower. However, now for the raw materials that are used to manufacture lithium-ion batteries, there has been a somewhat increase. in the price of lithium, and this is due to the demand that has come about due to more and more people wanting lithium-ion batteries for their solar systems, as well as the rise in electric vehicles. So this has brought about, there was a decline, then a very exponential increase in the price, rather in the demand of lithium. So this is the internal chemistry of the lithium-ion batteries, where we have two different reactions happening during discharge and during charging. However, the internal structure, we have the anode, which is a negative terminal that is a copper current collector, and we have the cathode, which is a positive terminal, being an aluminum current collector. Then we have a separator and an electrolyte. So during discharge, you'll have electrons moving from the negative terminal to the positive terminal, and we have the lithium ions that are moving between the anode and the cathode. And then during charging, the opposite happens. We have the ions, lithium ions, moving from the cathode to the anode. And now that is how a cycle during the charging and the discharging of a lithium-ion battery works. So you have the pros and cons of the lithium-ion batteries. They require almost no regular maintenance. They have a high energy density, meaning they can hold more energy in a smaller space as compared to a lead-acid battery. They have a longer life cycle. We've seen around, you can have even 10,000 cycles as compared to 700 cycles of the lead-acid battery. And this longer lifespan means or is due to the lithium-ion batteries having a higher depth of discharge. Then the disadvantages, they are more expensive compared to the lead-acid batteries. They have a higher chance of catching fire due to thermal runaway. This is when the temperatures exceed the limits that have been set. And one of the biggest disadvantages with this is that once a lithium-ion battery catches on fire, there is no way of putting it out. You'll have to let it burn itself out. Then there's you need an internal battery management system, a BMS, for the lithium-ion batteries, and they require protection from being overcharged and being completely discharged, meaning that they need to maintain the voltage and the current within safe limits. Then you have supercapacitors, and they have a very high capacitance and low voltage rating compared to the normal capacitors that we have in our electrical devices. So capacitors store energy in the form of an electric field, and this energy is stored between the ions of the electrolyte and the electrode. So it's a mix between, the supercapacitor is a mix between a battery and a capacitor. And we've seen a combination of supercapacitors and batteries being used as storage methods. But the supercapacitors really don't rely on the chemical reactions within the cells for them to function, but they use potential energy that has been stored electrostatically within them. So it is a purely electronic device. And this is what separates supercapacitors from other electrochemical batteries. However, they have a very low specific energy as compared to other batteries, and they are usually preferred for energy that is required in small bursts of power. So because you can have a very large supercapacitor with a lot of power, but it needs to be discharged very fast. So that is the application of the supercapacitor. So a fantastic example of how supercapacitors are being used is in Sweden, where they are used to charge hybrid buses between stops. So in just 15 seconds, you can top up the energy um, in the supercapacitor, and this can be used to power the vehicle to the next stop, where it is then topped up within seconds, and this energy can be used till the next stop. So in those instances where you need very fast charging and discharging, that is where the supercapacitors come in. So here we have batteries and capacitors, the pros and cons. So for the batteries, we looked at this earlier. We have better power density, better storage capabilities, better leakage, current leakage as compared to capacitors. They will not leak current as much as supercapacitors will, and they have a constant voltage that can be turned on and off. However, the cons are a limited cycle life, voltage and current limitations, because for some, especially for lead acid batteries, you only are limited to around 12 volts, 200 Ah, or 24 volts, 200 Ah. They have long charging times that can be detrimental to um, the capabilities in storage, and they are more temperature sensitive as compared to capacitors. Then for capacitors, we have long life cycle, high load currents. They have short charging times, and they are excellent. They have excellent performance in different temperatures. However, they have very low specific energy, so you cannot store a lot of energy in a smaller size. They have a linear discharge voltage, meaning you'll just get one rate of discharge, and then they have high self-discharge, where if they are not used, they can completely drain themselves out. And then they have a high cost per watt, meaning this will be a very expensive storage solution. Then now we look at lead carbon batteries. So a lead carbon battery is a mixture or a combination of a supercapacitor and a lead acid battery. And this is due to the internal connections that has been done. And we are going to look at it in the next slides. So it takes advantage of the instant power and large capacity charging of what supercapacitors have, and the advantage of having the high energy density of the lead acid batteries. So meaning can charge fully charge in 1 hour and has a good charge and discharge performance. So this is the internal structure of how a lead carbon battery looks like. We have the lead oxide positive plate that has then a separator and the lead negative plate. And then this now, when you add carbon onto the lead electrode, meaning now you're coating this this carbon negative plate, or rather this lead negative plate with carbon, and these carbon particles are added to the negative electrode to form a conductive layer, and this increases the pore size of the negative plate, allowing more acid or more electrolyte to pass through, and this means that you can have more energy being stored. So we had looked at this, the internal structure. So what the lead carbon battery is a modified version of the lead acid battery. So the addition of the carbon improves the charge and discharge cycles. And with that, this charge and discharge cycle can reach several times that of lead acid batteries. And this we've seen with lead acid batteries having around 700 to 900 cycles, and lead carbon batteries having around 3,500 cycles. And this is at around 50% depth of discharge. So you can see there is almost twice or thrice increase in life cycle just by modifying the internal structure of the battery. So what are the advantages of having lead carbon batteries? We have up to 10-year design life for lead carbon batteries, but this is when you're running it in the best case scenario in perfect conditions. This is compared to lead acid batteries that have around a 3 to 5 year design life. So we are talking about moving from 700 cycles to around 3,500 cycles. You can see that increase in the lifetime of the battery means that you'll be using that one battery for a longer period of time. You won't need to replace it within the time that you would have replaced the lead acid batteries. They have a much better and greater power storage capability per dollar as compared to lithium, meaning that you have approximately twice the storage capacity from lead carbon compared to lithium, which is about half the price for the same capacity. So looking at this, the best, or rather one of the ways to describe the performance of the lead carbon battery, comparing it to lead acid and to lithium ion, is that you have the storage capability and lifetime of a lithium ion battery with the price of a lead acid battery. Other advantages of the lead carbon battery compared to lithium or compared to lead acid is still it don't require a battery management system. There is no thermal runaway of individual battery cells. It has a much higher energy density and longer life. Um, this is compared to existing AGM and gel and flooded lead acid batteries, and they are suitable for both on-grid, hybrid, and off-grid systems due to their high current charge and discharge capacities. Then now we look at the applications of the lead carbon batteries. So as Jubaili Grow Solar, we have a new residential solar hybrid solution that we are bringing into the market. And with this, we are incorporating the lead carbon battery. So with this, we have a Jubaili branded inverter charger. So this is a hybrid inverter that can take inputs from the grid, from the generator, from solar, and from the battery, and this can be used to power the loads. So we are not only just bringing the battery itself, however, we are providing a whole residential solution with this. And so these are some of the features of the inverter charger that we have that will work with the lead carbon battery. It has an integrated Bluetooth interface with an Android app, and it supports on-the-go USB function, meaning you can upload data and download data into a USB drive. It has a detachable LCD control module that can be taken up to 20 meters away. So with this, you can have the inverter outside, and then you can have the LCD display somewhere indoors where you can easily see the parameters of your entire residential system without needing to go to where the inverter is. Then it has a battery equalization, which will help increase the life cycle of the battery. So it has an inbuilt battery equalization function that removes sulfation to optimize battery performance. So one of the major disadvantages of lead acid batteries is a phenomenon called as sulfation, where due to the sulfuric acid that is used inside the battery, it forms a layer on the negative electrode of the lead acid battery. and that prevents the storage of energy within the battery. So means due to that layer of sulfur building up, the lead acid battery is not able to store as much charge as it should have. And this also significantly reduces the battery life. However, with lead carbon batteries, due to the addition of the carbon layer, this prevents sulfation from taking place, meaning now that you have a better um, performing battery that will last longer. And then now that added to this system and the battery having or rather the inverter having a battery equalization function, it means that it will extend the lifetime of your battery even further when you're using the lead carbon batteries. Then images are not very clear, but it also supports battery independency, where the inverter can keep supplying power to the loads from the PV or from the grid without the battery being connected. However, for in the hybrid solution, when you have the batteries, you have more options for where your power is coming from. Then we have it has a replaceable fan design and a user-friendly LCD operations. So with this, we have another webinar on the residential systems where we go deeper into these solutions. And these are some of the applications of this inverter charger that we have. So thank you very much. We'll go through the questions that that are being asked. Kindly remember to mark your questions so that you'll be able to see them when you're doing the Q&A. Kindly share lithium cell specs. This will be shared to you at the end of the webinar. Kindly share the materials and audio after the session. You will get this presentation at the end of the webinar using the email address that you used to register. Kindly request the capacity of lithium batteries, store energy for 36 kilowatt hour peak from panels to run loads for about 8 hours per day. So this question will require to do a bit of design calculations. So you can reach out to me to the email that was that this technical solutions or JB Solar, and you'll be able to guide through the design of energy storage. Start with which one is the best to practice for battery connection when you have a battery bank and are connected to more than two inverters in parallel mode using bus bar or joining the cables. What are the most common, that is number one. Number two, what are the most important parameters to look for when selecting battery for backup system? Then number three, how does the balancing system work? Please explain. So question number one, which is the best to practice for battery connection? So it begins with how you've done your design. If you have two inverters in parallel, the best way will be to use bus bar, because this will first reduce your cabling costs. DC cables are among the most expensive cables, so using a bus bar is a better option as compared to joining cables, because even with joining cables, you have some losses that will occur within the cables. Then what are the most important parameters to look for when selecting a battery for a backup system? So number one, is the capacity. of storage that you require, you might find it will be better to go with lithium or with the lead acid. Then you have the cost. We've seen that for lithium-ion batteries, they are a bit more expensive as compared to the lead carbon or the lead acid batteries. So the important parameters also to look at the energy density, but all this will be dictated by cost and the design that you have for your backup. How does the balancing system work? I believe this is the battery equalization. So it will try to equalize the current and the voltage to make sure that it's operating optimally. I hope that has answered your question. What are the max capacity in terms of kilowatt hours of supercapacitor can be available in the market, and are they suitable for mini grids? So for mini grids, the best application or the best battery chemistry will be either the lead acid or the lithium ion batteries, because you need to store charge or you need to store energy over an extended period of time, and you need to monitor how that energy is being um, utilized in terms of charge and discharge. However, the max capacity, this I'm not quite sure, because we've seen some go from as small as 5 kilowatt hours, going up to some with megawatt range. However, for mini grids, I think what has been developed has been with the lithium ion or the lead carbon. However, we are still seeing new energy storage methods coming in, especially for mini grids. So I'm sure there are companies that are developing higher capacities for supercapacitors. What is the cycle life at 80% DOD of your lead carbon batteries? At 80%, I think the cycle life is around 4,500 cycles. However, I'll need to check with the data sheet, of which we can share with you, that shows the cycle life versus the DOD. Does the addition of carbon to the lead reduce the number of times the battery acid H2O level refill? With this lead carbon batteries, they do not have the liquid acid. They have a gel type acid. So this means that you also don't need to refill this electrolyte. Supercapacitor can be requested for customer for solar installations. Unfortunately, we do not deal in supercapacitors, but you can look out for other distributors and manufacturers who are dealing with supercapacitors. There's one who hadn't marked theirs as a question. How many hours for charging is required for a full charge of the lead carbon battery? So charging and discharging cycles are dependent on how you have designed your load. So a lot with the load, with the usage will determine how the charging and discharging will occur. So there are a lot of aspects that will determine how long a battery will charge and how fast the battery will discharge. Please share carbon battery specifications. Kindly reach out to us on the emails um, at the end of the presentation, and we'll be able to share all these technical specifications. Be on the lookout for a webinar next week on residential hybrid solutions, where we'll be talking about the one that I had introduced that has the lead carbon battery, and then we have another solution that uses the lithium ion batteries. What do you recommend on the voltage of battery selection for mini grid? 48 volt or higher? Now, with this, we've seen, especially for mini grids, operating between 24 and 48 volt voltages. So I think this is dependent on the requirements of the mini grid. What is the resistance, load, and voltage drop of the lead carbon battery? I can send you the details of the lead carbon batteries, the data sheet that shows this information. All right. Thank you very much for attending today's webinar. We'll come to the end. Before we exit, I'd like to put up a survey. Kindly fill it in. I'll have it up for around 5 minutes. Then we can end the webinar after that. Thank you very much. Once again, to the people who joined after I started, my name is Kennedy Kibetu, the technical engineer at Jubaili Brew Solar.